Could everything we see be a holographic image? This isn't a scene from a science fiction movie, but a profound idea at the forefront of theoretical physics, the holographic principle. It challenges our most fundamental understanding of reality, suggesting that the universe, in its entirety, might be a hologram. For centuries, our perception of the world has been rooted in three spatial dimensions. We move left and right, forward and backward, and up and down. This intuitive understanding is so deeply ingrained that it forms the bedrock of classical physics, from Newton's laws of motion to Einstein's theory of relativity. We describe the positions of objects using three coordinates, and we visualize forces and fields extending through this three-dimensional space. Even the most complex phenomena, like the intricate dance of planets around a star or the swirling chaos of a hurricane, are modeled and understood within this familiar framework. But what if this seemingly self-evident reality is, in fact, an elaborate illusion? What if the depth we perceive is not an intrinsic property of the universe, but rather an emergent phenomenon arising from a flatter, two-dimensional substrate? To grasp this radical concept, let's first consider how our own perception can be fooled. Think about a conventional hologram, the kind you might find on a credit card or a driver's license. It's a flat, two-dimensional surface, yet when illuminated correctly, it projects a stunningly realistic three-dimensional image. You can even move your head and see different perspectives of the object, just as if it were truly there in space. The entire three-dimensional scene is encoded within the patterns etched onto that flat surface. The information isn't lost, it's simply stored in a different, more compact form. Now, scale that idea up vastly. Imagine that the entire universe operates on a similar principle. This isn't to say that we're living inside a giant credit card, but rather that the fundamental constituents of reality might reside on a distant, two-dimensional boundary, and what we experience as three dimensions is merely a projection, a cosmic illusion. This idea, while seemingly fantastical, stems from deep theoretical puzzles in physics, particularly those arising from the study of black holes. Our understanding of dimensions has evolved considerably throughout history. Euclid formalized geometry in three dimensions, and for millennia, this was the undisputed truth. However, with the advent of Einstein's theory of special relativity, time was woven into the fabric of space, creating a four-dimensional space-time continuum. This wasn't just a mathematical trick. It fundamentally changed how we perceive events and their relationships. Later, string theory and M-theory introduced the concept of extra-spatial dimensions, curled up so tiny that we don't perceive them directly. These theories suggest that our universe might actually have 10 or 11 dimensions, with only 4, 3 spatial and 1 temporal, being readily apparent to us. But the holographic principle takes a different tack, suggesting that the effective number of dimensions might be fewer than we perceive, not more. The roots of this revolutionary idea can be traced back to the work of Jacob Bekenstein and Stephen Hawking in the 1970s, who investigated the thermodynamics of black holes. Black holes, as you know, are regions of space-time where gravity is so intense that nothing, not even light, can escape. They are often depicted as cosmic vacuum cleaners, swallowing everything in their path. However, Bekenstein made a groundbreaking proposal. Black holes have entropy. Entropy is a measure of disorder or the amount of information contained within a system. This was a radical idea because, according to classical physics, black holes were thought to be incredibly simple objects, characterized only by their mass, charge, and angular momentum. They had no hair, as the saying goes. Bekenstein's insight was that if a black hole has entropy, it must also have a temperature and radiate energy, albeit very slowly. This led to Hawking's famous discovery of Hawking radiation, which predicts that black holes slowly evaporate over time. But the most astonishing part of Bekenstein's discovery was how this entropy scaled. For ordinary objects, entropy is proportional to their volume. If you double the volume of a gas, you double its entropy. However, Bekenstein found that the entropy of a black hole is not proportional to its volume, but to the area of its event horizon, the boundary beyond which nothing can escape. This was a profound clue. It suggested that the information content of a three-dimensional region of space, the interior of the black hole, could be entirely encoded on its two-dimensional boundary, the event horizon. It's as if all the books in a vast library could be perfectly summarized and stored on the library's outer walls. This seemingly counterintuitive result sparked the initial seeds of the holographic principle. It implied that there might be a fundamental limit to how much information a region of space can contain, and that this limit is set not by its volume, but by its surface area. Consider this analogy. Imagine a computer screen. It's a two-dimensional surface, yet it can display incredibly complex and detailed three-dimensional worlds in video games or simulations. All the information needed to render those 3D environments is encoded in the 2D pixels on the screen. The holographic principle suggests something similar for the universe itself. The pixels of our universe might reside on a distant, two-dimensional boundary, and our perceived three-dimensional reality is the display. This idea gained further traction with the work of Gerard T. Hooft and Leonard Susskind, who independently developed and formalized the holographic principle in the 1990s. They argued that the maximum amount of information that can be contained in a region of space is proportional to the area of its boundary, not its volume. This principle has profound implications for our understanding of gravity, quantum mechanics, and the very nature of reality. It suggests that our universe, with all its stars, galaxies, and conscious beings, could be a projection from a lower dimensional reality. The holographic principle is not just a philosophical musing. It's a powerful theoretical tool that attempts to reconcile two of the most successful, yet seemingly incompatible, theories in physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels. One of the biggest challenges in modern physics is to unify these two theories into a single, coherent framework of quantum gravity. The holographic principle offers a potential pathway to this unification by suggesting a deep connection between gravity in a higher dimensional space and quantum field theories in a lower dimensional space. So, when we talk about the illusion of three dimensions, we're not suggesting that your hand isn't real or that the chair you're sitting on is a figment of your imagination. Rather, we're exploring the possibility that the fundamental nature of reality, the way information is truly stored and processed in the universe, might be inherently two-dimensional, and our experience of three spatial dimensions is an emergent property, a highly convincing projection. This is a concept that pushes the boundaries of our intuition and forces us to reconsider what we truly mean by reality. It's a journey into the heart of the cosmos, where the familiar becomes strange, and the seemingly solid world around us might be a magnificent, cosmic hologram. This concept of a holographic projection becomes even more profound when we consider the enigmatic nature of black holes, which represent the ultimate limits of information storage and retrieval in our universe. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses a boundary called the event horizon. This event horizon isn't a physical barrier, but rather a point of no return where the escape velocity exceeds the speed of light. For decades, black holes have presented a profound challenge to our understanding of physics, particularly concerning the fate of information. This challenge is known as the black hole information paradox. The paradox arises from a fundamental conflict between two pillars of modern physics: general relativity and quantum mechanics. General relativity describes black holes as incredibly simple objects, characterized only by their mass, angular momentum, and electric charge. a concept famously known as the no-hair theorem. This theorem suggests that any other information about the matter that forms a black hole, or falls into it, is lost forever once it crosses the event horizon. Imagine throwing a book into a black hole. According to the no-hair theorem, the black hole wouldn't retain any information about the specific words, pages, or even the type of paper the book was made from. It would only gain a tiny bit of mass, charge, and angular momentum. However, quantum mechanics dictates that information cannot be truly destroyed. Every physical process, in principle, should be reversible, meaning the initial state of a system can always be determined from its final state. This principle, known as unitarity, is a cornerstone of quantum theory. Stephen Hawking's groundbreaking work in the 1970s further deepened this paradox. He showed that black holes aren't entirely black. They emit a faint thermal radiation, now known as Hawking radiation, and slowly evaporate over time. The problem is that Hawking's calculations suggested this radiation is purely thermal, meaning it carries no information about what fell into the black hole. If a black hole eventually evaporates completely, and the Hawking radiation contains no information about its past, then all the information about everything that ever fell into it would seemingly vanish from the universe. This would be a direct violation of quantum mechanics' fundamental principle of information conservation. The black hole information paradox thus posed a serious dilemma. Either general relativity's description of black holes as information-destroying entities was incomplete, or quantum mechanics' principle of information conservation was wrong. For decades, physicists grappled with this profound inconsistency, realizing that a resolution would require a deeper understanding of how gravity and quantum mechanics intertwine. Intriguingly, the very properties of black holes that led to this paradox also offered a crucial clue. In the early 1970s, Jacob Bekenstein proposed that black holes must possess entropy, a measure of disorder or, more fundamentally, a measure of the information contained within a system. Classically, black holes were thought to have no entropy, but Bekenstein realized that if you throw something with entropy into a black hole, and the entropy simply disappears, it would violate the second law of thermodynamics. To preserve this fundamental law, black holes themselves must have entropy. Bekenstein's revolutionary insight was that this entropy is proportional to the surface area of the black hole's event horizon, not its volume. This was a radical idea, as entropy in ordinary physical systems is typically proportional to volume. Later, Stephen Hawking confirmed this by calculating the exact value of black hole entropy, now known as Bekenstein-Hawking entropy, showing it to be precisely 1/4 of the event horizon's area in Planck units. This area-dependent entropy was a crucial step towards the holographic principle. It implied that the maximum amount of information that can be contained within a region of space is not limited by its volume, but by the area of its boundary. For a black hole, all the information about the matter that has fallen in appears to be encoded on its two-dimensional event horizon. From the perspective of an outside observer, objects approaching a black hole appear to slow down and become smeared out across the event horizon, never actually crossing it due to the extreme time dilation. This suggests that the information isn't truly lost, but is somehow imprinted on this boundary. This idea of information being stored on a surface rather than within a volume is precisely the essence of the holographic principle. It suggests that a three-dimensional region of space, like the interior of a black hole, can be fully described by information residing on a two-dimensional surface. In the context of the information paradox, this means that the information about everything that falls into a black hole might not be destroyed, but rather preserved as bits on the event horizon. Each bit of information corresponds to a Planck area on the holographic screen of the black hole horizon. This provides a potential resolution to the paradox, suggesting that information is not lost, but merely transformed and stored in a different, lower dimensional form. The holographic principle, inspired by black hole thermodynamics, offers a way to reconcile the seemingly contradictory demands of general relativity and quantum mechanics. It suggests that the information isn't truly swallowed and gone forever, but rather remains accessible, albeit in a highly scrambled and encoded form, on the boundary of the black hole. This radical shift in perspective from a volumetric to a surface-based understanding of information is a cornerstone of the holographic principle and has profound implications for our understanding of reality itself. The concept of the holographic principle, this revolutionary idea that information about a 3D space can be encoded on a 2D surface, didn't appear out of thin air. It emerged from a series of profound theoretical breakthroughs related to black holes, challenging our fundamental understanding of information, gravity, and reality itself. The story truly begins with Jacob Bekenstein in the 1970s. He made the astonishing realization that black holes must possess entropy. This was a radical idea because entropy is a measure of disorder or, more precisely, the number of possible microscopic arrangements that correspond to a given macroscopic state. In essence, it quantifies information. If black holes have entropy, it implies they contain information. Bekenstein even calculated this entropy, finding it to be proportional to the surface area of the black hole's event horizon, not its volume. This was a crucial departure from what one might intuitively expect for a three-dimensional object. Shortly after, Stephen Hawking entered the scene with his groundbreaking discovery of Hawking radiation, demonstrating that black holes aren't entirely black, but slowly evaporate by emitting particles. This led to the infamous black hole information paradox. If black holes evaporate completely, and Hawking radiation carries no information about what fell in, then what happens to all the information that went into forming the black hole? Quantum mechanics dictates that information cannot be truly lost. It can be scrambled or encoded, but never destroyed. This apparent conflict between general relativity, which describes black holes, and quantum mechanics became one of the most significant puzzles in modern physics. This paradox set the stage for the holographic principle. Gerard T. Hooft, in 1993, took Bekenstein's ideas further. He proposed that the information of particles falling into a black hole isn't lost, but is imprinted on the event horizon itself. He suggested that these infalling particles cause gravitational deformations, creating bumps on the horizon that effectively encode their information, which can then be transferred to the outgoing Hawking radiation. This provided a mechanism for how the event horizon could completely describe the black hole's contents, essentially treating a three-dimensional system, the black hole's interior, as being fully described by information on its two-dimensional boundary, the event horizon. Building upon T. Hooft's insights and Bekenstein's work, Leonard Susskind further developed the holographic principle. In 1995, he articulated the idea that the entire universe could be understood as a hologram, where all the information making up our three-dimensional reality is encoded on a distant two-dimensional surface, a cosmological boundary. Susskind argued that the oscillations of a black hole's horizon could offer a complete description of both infalling and outgoing matter, drawing parallels to how string theory, in certain formulations, provides a lower-dimensional description from which gravity emerges. He famously stated, "The three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface." The holographic principle, therefore, postulates that a theory of gravity describing a region of space can be considered equivalent to a theory defined only on the surface area that encloses that region. This means that the maximum amount of information a space can contain is related to the area of its boundary, not its volume. This radical proposition, that the number of variables needed to describe a region of space grows with its surface area rather than its volume, challenged conventional physics, where the information content typically scales with volume. It offered a potential resolution to the black hole information paradox by suggesting that information is not destroyed, but rather smeared across the black hole's boundary. This conceptual framework laid the groundwork for a profound shift in how physicists view the fundamental nature of space-time and information. The conceptual framework of holography, suggesting that information within a volume of space might be entirely encoded on its boundary, truly found its concrete realization in the anti-de Sitter/conformal field theory, AD/CFT correspondence. Proposed by Juan Meldacena in 1997, this groundbreaking conjecture posits a profound and exact equivalence, or duality, between two seemingly disparate types of physical theories. On one side of the correspondence, we have a theory of quantum gravity, often formulated within the framework of string theory or M-theory, existing in a specific type of curved spacetime known as anti-de Sitter space, ADS. Anti-de Sitter space is a mathematical model of spacetime with a constant negative curvature, unlike our own universe which, at large scales, appears to have a small positive cosmological constant. While not a perfect description of our universe, AD space serves as a crucial theoretical laboratory for exploring quantum gravity. In this higher-dimensional bulk spacetime, gravity is an active force, and objects like black holes exist and behave according to the laws of general relativity. On the other side of the correspondence lies a conformal field theory, CFT, which is a quantum field theory without gravity, living on the lower dimensional boundary of that anti-de Sitter space. Imagine this boundary as a flat, gravity-free spacetime where physics is governed solely by the principles of quantum mechanics. Conformal field theories are particularly symmetric and mathematically well-behaved quantum field theories, often studied in contexts ranging from string theory to statistical mechanics. The conformal aspect means these theories are invariant under transformations that preserve angles, though not necessarily distances or scales. The astonishing claim of AD/CFT is that these two theories, despite living in different numbers of dimensions and describing vastly different physical phenomena, one with gravity, one without, are fundamentally equivalent. There's a dictionary that translates every entity and calculation in one theory into a counterpart in the other. If you have a question about the physics happening in the higher dimensional anti-de Sitter bulk, you can translate it into a question in the lower dimensional conformal field theory, solve it there, and then translate the answer back to get the exact same result you would have obtained directly in the gravitational theory. This makes the AD/CFT correspondence a strong weak duality. When the gravitational theory is weakly interacting and mathematically tractable, the dual quantum field theory is strongly interacting and vice versa, offering a powerful tool to study problems that are otherwise intractable in either framework alone. One of the most celebrated examples of this correspondence is the duality between type IIB string theory in 5-dimensional anti-de Sitter space multiplied by a 5-dimensional sphere at S5 times S, and a 4-dimensional n equals 4 supersymmetric Yang-Mills theory on its boundary. In this specific instance, the gravitational theory effectively lives in 5 dimensions, with the 5 additional compact dimensions of the sphere curled up. While this particular example doesn't directly describe our 4-dimensional universe, it provides a robust and well-studied model for understanding the principles of the correspondence. The ADS/CFT correspondence is often described as a holographic duality because it mirrors the way a 2-dimensional hologram encodes all the information of a 3-dimensional object. The conformal field theory acts like this hologram, capturing all the information about the higher-dimensional quantum gravity theory. This implies that the higher-dimensional geometry of the anti-de Sitter space is not fundamental, but rather emerges from the quantum states and interactions of the lower dimensional boundary theory. In essence, space-time and gravity themselves can be viewed as holographic projections of underlying quantum information. This duality has profound implications, particularly for the black hole information paradox. As we discussed, Stephen Hawking's calculations suggested that black holes destroy information, seemingly violating a fundamental principle of quantum mechanics known as unitarity. However, the AD/CFT correspondence offers a powerful potential resolution. Within this framework, black holes existing in anti-de Sitter space correspond to specific configurations of particles on the boundary of that space. These boundary particles, governed by the rules of quantum mechanics, evolve in a unitary fashion, meaning information is conserved. Therefore, the black hole in the higher dimensional space must also evolve unitarily, preserving information. In 2004, Stephen Hawking himself conceded that black holes do not violate quantum mechanics, influenced by the implications of the ADS/CFT correspondence. He even suggested a concrete mechanism by which quantum perturbations of the event horizon could allow information to escape, thereby resolving the paradox. The correspondence implies that the thermal radiation emitted by black holes, Hawking radiation, is not entirely random, but contains subtle quantum correlations that encode information about the black hole's interior. Recent research, particularly in 2019, has further supported this by amending calculations of Hawking radiation entropy in certain models, showing that the radiation is indeed dual to the black hole interior at late times. Beyond resolving the black hole information paradox, the AD/CFT correspondence provides a powerful toolkit for studying strongly coupled quantum field theories, which are notoriously difficult to analyze using traditional methods. Problems in nuclear and condensed matter physics, such as understanding the behavior of the quark-gluon plasma created in particle colliders or the properties of certain high-temperature superconductors, can be translated into more mathematically tractable problems in string theory within the ADS bulk. This has led to remarkable insights and even some results that are surprisingly close to observed properties of matter. The correspondence also offers geometric formulas for quantum information measures, such as the Ryuta-Yanagi prescription for entanglement entropy, directly linking space-time geometry to entanglement structure. This suggests that the very fabric of space-time might be intricately woven from quantum entanglement on the boundary. The implications of the holographic principle are truly profound, reshaping our understanding of reality, quantum gravity, and even the nature of information itself. If space-time is indeed woven from quantum entanglement on a boundary, as the Ryuta-Yanagi prescription suggests, then our perception of a three-dimensional universe could be an emergent phenomenon, a sophisticated illusion projected from a lower-dimensional reality. This isn't to say our reality isn't real, but rather that its fundamental nature might be different from what we intuitively perceive. One of the most significant implications of the holographic principle is its potential to unify quantum mechanics and general relativity, two pillars of modern physics that have long resisted reconciliation. General relativity excels at describing gravity and the cosmos on large scales, while quantum mechanics governs the subatomic world. The holographic principle, particularly through the ADS/CFT correspondence, offers a framework where a theory of quantum gravity in a higher dimensional spacetime can be equivalent to a quantum field theory without gravity in a lower dimension. This duality provides a Rosetta Stone for translating between these seemingly disparate descriptions, suggesting that gravity might not be a fundamental force but an emergent property arising from the underlying quantum system. This shift in perspective offers a promising pathway to developing a consistent theory of quantum gravity, one that avoids the singularities and infinities that plague traditional approaches. The holographic principle also offers a compelling resolution to the black hole information paradox. Hawking's initial calculations suggested that information falling into a black hole would be lost forever as the black hole evaporated, violating a fundamental principle of quantum mechanics known as unitarity, which states that information cannot be destroyed. However, the ADS/CFT correspondence demonstrates how black holes can evolve in a manner consistent with quantum mechanics. In this holographic picture, the information about what falls into a black hole is not lost, but is instead encoded on the black hole's event horizon, which acts as a holographic screen. This information is preserved in the dual quantum field theory on the boundary, ensuring that unitarity is maintained. Stephen Hawking himself conceded in 2004 that information is conserved, attributing the resolution to the ADS/CFT correspondence. Beyond these profound implications for fundamental physics, the holographic principle sparks intriguing questions about the very nature of information and its role in the universe. It suggests that information, rather than matter or energy, could be the most fundamental building block of reality. The universe might encode all its details on a cosmic boundary, much like a hologram stores three-dimensional information on a two-dimensional surface. This aligns with the growing importance of information theory in physics and suggests that space and time themselves might emerge from this encoded information. The concept of an emergent space-time from entanglement also opens doors to reconsidering our perception of reality. If our three-dimensional world is a projection, then our sensory systems, which have evolved to interpret and navigate this perceived 3D world, might be optimized for decoding holographically encoded data. Optical illusions and other cognitive biases could be seen as revealing the limitations of our decoding capabilities, suggesting that we may only perceive a subset of the information encoded in the universe. Some even speculate about the connection between the holographic principle and consciousness, suggesting that consciousness itself might emerge from resonant interactions between brain activity and a higher dimensional holographic information field. While the holographic principle is a powerful theoretical framework, it remains a subject of active research and debate. The ADS/CFT correspondence is the most concrete realization of the principle, and while it has provided considerable evidence for its correctness, it has not yet been rigorously proven. Furthermore, the ADS/CFT correspondence applies to anti-de Sitter space, a universe with a negative cosmological constant, which is different from our own expanding universe with a positive cosmological constant. Therefore, whether the holographic principle applies to our universe in its entirety and how it does so remains a central open question. Experimental verification of the holographic principle is a formidable challenge, and direct observation of quantum gravity effects is still beyond our current technological capabilities. However, scientists are exploring various avenues. Some researchers are investigating whether space-time might not be perfectly smooth if the universe is holographic, looking for tiny imperfections or holographic noise that would be incredibly small and difficult to measure. Others are attempting to create mini-universes in the lab to study how gravity and space could emerge from quantum particles. There have been experiments, like Fermilab's holometer, designed to look for such holographic noise, though they have so far yielded no evidence. However, some experts argue that these experiments may not be testing the holographic principle in the way it is understood within the theoretical community. The ongoing research into the holographic principle continues to push the boundaries of our understanding of the cosmos. It's a journey that challenges our most fundamental assumptions about space, time, and reality itself, inviting us to consider a universe where the familiar three dimensions might be a magnificent, emergent tapestry woven from the intricate dance of quantum information on a distant, unseen boundary. This paradigm shift holds the promise of a unified theory of everything, a deeper understanding of black holes, and perhaps even new insights into the very nature of consciousness. The future of reality, viewed through the lens of the holographic principle, is a captivating frontier of scientific exploration.